Hello folks, it's Mr. Vast back with another award-winning video. This one for Chapter 6, Section 6.5 in our College Credit Plus College Algebra course. So this section is titled Applications of Exponential and Logarithmic Functions. And what you see on the screen here is page 1 of a handout that you should have picked up in class that basically contains every equation that you could need for one of these application problems. Page 2, the back side of it, contains 5 examples that I'm going to go over with for you in this video. One thing I want to begin with here is that the key to this section is basically these are word problems, and I know that a lot of you kind of get a little bit of stage fright with word problems because they're challenging. You don't necessarily know exactly what to plug into where and what you're supposed to be solving for. And that's the real art of problem solving, is to be able to read a word problem, figure out what's being asked, what equation or formula you need and to get there. So that's what we're going to kind of hope that we can get better at through this section. And the examples that I put together are ones that mirror what you'll see in WebAssign, and they should help you get through the Section 6.5 WebAssign successfully. All right, let's take a look at this first couple of equations here. We have compound interest, continuously compounded interest, uninhibited growth or exponential growth, and then radioactive or exponential decay. And then right below that we have Newton's law of cooling. What I want to highlight about these 5 formulas is that they're all exponential functions. So you have some quantity equals some amount times something raised to an exponent. Okay, that's in the form of an exponential function. We have, like here for continuously compounded interest, we have some quantity equals a principal amount times e raised to the RT. Over here in this column, I give a description of all the different parameters, all the different quantities that go into this formula. Let's look here at uninhibited or exponential growth. I have some quantity equals an initial amount times e to the kt. I hope you can look at these formulas right here, these 3, and kind of say, those pretty much look like the same formula. That's because they are. The only way they differ is what each of these initial quantities is. This one happens to be an initial invested amount. This one here is an initial quantity that's growing. This one here is an initial amount that's decaying. So there are similarities between all these formulas, and I hope you're able to see that. Moving down to some of the formulas at the bottom of the page. Some of these are really obscure. I'm going to be honest with you. You're probably not going to... I can't picture you necessarily looking at the intensity of sound outside of maybe if you're a sound engineer, but we are going to do a problem like that just so that you're familiar with it when you get to WebAssign. Again, all of these formulas here, if you take a look at them, we've moved out of the realm of exponential functions and into the realm of logarithmic functions. So these are going to be different types of application problems. So exponential functions, logarithmic functions, different applications. Let's go with number 1. Okay, folks, here's question number 1, and what I'm not going to do here for you is read each question to you. I'll let you pause the video and do that, or look at the worksheet you grabbed in class. And this one, let's go ahead and talk about the critical information here. So we have an initial quantity here. We also have an interest rate here, and that's compounded monthly. Okay, now that interest rate is written as a percent. We're going to need to remember that as a percent, that's going to be 0.0045. All of our rates we're going to need to express as a decimal, not as a percent. Okay, so part A of this question, how much will he have after 6 years? Let's take a look at the interest equation. So we have interest or amount at time t equals principal times 1 plus rate over n, where n is the number of periods, raised to the n times t power. So let's go ahead and figure out which of these quantities goes where. All right, so for part A of this problem, we're asked for the amount of money after 6 years. In this problem, time is in years, and the same in this formula, is going to be our principal amount, $5,000, times 1 plus our interest rate, 0.0045, divided by the number of periods per year. Well, since we're compounded monthly, that number is 12. What this does inside parentheses here is it gives us a multiplier or a growth factor for our exponential growth function. If we take 1, that's kind of like our principal amount, plus the amount of interest we earn per period. That's this 0.0045 divided by the number of periods per year. This gives us our growth factor. We now raise that to the n times t power. Well, we have n is 12 because we're compounding 12 times per year, and we're doing this, our t is 6 for 6 years. After you go ahead and run this through your calculator, you'll get an amount of $5,136.81. For part B, we need to use a different formula because we're asked how much more would be in the account if it earned 0.45% compounded continuously. Well, we have the same rate, that 0.0045, but we have what is often known as the PERT equation. So continuously compounded interest grows as follows: principal times e raised to the RT power. Remember, e is our base of our natural logarithm, which is about 2.7182. So for this problem, the amount after 6 years will be the principal times e raised to the 0.0045 times 6. And when you run that through your calculator, you will get an amount of $5,136.84. So we do have to make sure we go back and answer the question. What's the difference between this amount and the amount in part A? Well, it looks like we would earn 3 cents more if we were in the account that was compounded continuously. For part C, this one's a little bit of a curveball, folks. It says, how long would it take the net worth of his investment, remember that was $5,000, how long would it take that to grow by at least $1,000 with monthly compounding? Well, to grow by $1,000, that means he has to have $6,000. So I need to take this equation here and rewrite it. It's going to look like this. It's going to be $6,000. That's the amount we're going to have after some time. Has to equal $5,000 times 1 plus 0.0045 over 12 raised to the 12t. And t is what we're trying to find here. And we've done enough problems like this over the last week or so that I hope you remember, if your variable is in the exponent, you're going to need a logarithm. So we're going to need to do some rearranging here and eventually take a log of both sides so that we can get t all by itself. The first thing I'll do, though, is I'll divide both sides of this equation by 5,000. So if I divide this side by 5,000 and this side by 5,000, then these two 5,000s are gone. And what I'm going to have after I cancel out some zeros is something that looks like this. 6 over 5 equals 1 plus 0.0045 over 12 raised to the 12t power. So this amount I have inside parentheses here, this 1 plus 0.0045 over 12, I might as well go ahead and just write the decimal equivalent for that right now and clean this problem up a little bit. So that's going to be, if you plug that into your calculator, you're going to get 1.000375. At this point, I'm ready to take the natural log of both sides. When I do that, I'm going to get the following equation. I'm going to get the natural log of 6/5 equals 12t. And folks, I'm running out of room. Let's move this down here. ln of 6/5 equals 12t times the natural log of 1.000375. At this point, this problem becomes an algebra 1 problem. I have some number equals 12 times t times some other number. So in order to get t all by itself, I need to divide both sides of this equation by 12 times the ln of this long decimal here. So what is that going to look like? It's going to look like this. T equals the ln of 6/5 divided by 12 times the natural log of 1.000375. And after you plug that into your calculator, you're going to get an answer of about 40.5 years. So based on this meager interest rate compounded monthly, if you want your money to grow by only $1,000, it's going to take a long time. One thing I want to point out here is this equation right here, or this expression, when you plug this into your calculator, you need to be really careful. If you're not careful, then you might end up multiplying by the ln of 1.00375 rather than dividing by it. So make sure you try this one out on your calculator and you can see, you can get the same answer that I do. We have one more problem here, one more part of this problem, and that is part D. It reads, if he wants $7,000 in 3 years, how much would he need to invest at the start? So again, this is kind of another curveball problem. It's a little bit different than just a straight plug and chug. So let's see if we can set this up. If he wants $7,000 in 3 years, how much would he have needed to start with? So in this problem, I'm given everything except the principal, except the starting amount. And this one is actually easier than the previous one because I don't need to take a logarithm to get the answer to this. I just need to divide both sides of the equation by this. So that's going to give me P equals 7,000 divided by, remember this here was 1.000375 raised to the 12 times 3 or 36th power. After you plug that into your calculator, you're going to get an answer of about $6,096.15.